we have looked at waves in general, and now we will look at sound. Sound is a longitudinal wave. So it propagates through different media. If you remember that the longitudinal waves count on the fact that the particles in the medium are close together, and as the particles move longitudinally in the direction of propagation of the wave, they bump against other particles, and that's how the sound gets propagated. The speed of sound is square root of bulk modulus divided by the density of the medium. So the bulk modulus is a measure of incompressibility of a medium, and rho is the density of the medium. So the sound propagates faster, has a higher speed in solids than less fast in liquids, and they propagate the slowest in gases. There are certain characteristics of sound that are subjective qualities. So pitch and loudness are subjective. People hear pitch and loudness differently depending on age and whether their ears work properly or not. But these quantities, pitch and loudness, do correspond to quantitative characteristics. And those characteristics are frequency and intensity. So high-frequency sounds are perceived as high-pitched sounds, and the range of audible frequencies for humans is 20 hertz to 20 kilohertz. This is for a healthy young person. The older the person gets, the smaller this range becomes. Typically, it's the high-frequency sounds that cannot be heard so well anymore. Then high-intensity sound is perceived as a loud sound, and the intensity of the softest sound that one can hear is called the threshold of human hearing, and that is 1 times 10 to the negative 12th watts per square meter. Now, the intensity of sound has to do with the amplitude of the sound wave, and it is also the power transported by the sound wave per unit area. So if we have a source of sound, we know that the sound will propagate radially outward. So if that sound has a certain power, if we divide that power by the area that it propagates through, we get the intensity of the sound. So the area for a sound propagating uniformly in all directions would be the area of a sphere, the surface area of a sphere. So that is 4 pi r squared. But if we're looking at the power that the eardrum gets, so then power would be area times intensity. In that case, the area is the area of a circle, so it is just pi r squared. So depending on the wording of the problem, the area can either be the area of a sphere or the area of a circle. The range of intensities of sound is very large, starting at the threshold of human hearing, 1 times 10 to the negative 12th watts per square meter. So then when we want to compare sound intensities, we have to use a logarithmic scale. The sound level is beta, and it's measured in decibels. So we're using the sound level to compare sound intensities. So the equation for the sound level is 10 decibels times log of the intensity of a sound divided by the threshold of human hearing. So this part becomes the comparison I over I naught, but then we're using a logarithmic scale because we're dealing with really high powers, 10 to the negative 12th, and that goes all the way down to 10 to the 0th, and then all the way back up to 10 to the 4th. So the range is really, really huge here. So that's why we're using a log base 10 scale to find the sound level, which compares the two sound intensities. Now, we want to look at standing waves on a string, and in a little bit also standing waves in a pipe. So first we have to define a few things. There are things like nodes and antinodes. Nodes are the points on a standing wave that are not displaced from equilibrium, and the antinodes are points on a standing wave that are displaced at maximum amplitude. So let's look at a standing wave, and here we have a standing wave that's bounded. So at the boundary we have nodes. So here is the first pattern that wave can make. So there will be a node at either end and an antinode where the displacement here is largest. Then a second pattern that this can form looks something like this. So there's a node there, a node here, a node there, and then we have antinodes here and here. And of course my drawing is not very good. This node should be like right in the middle here. I'll try to do the next one a little bit better. So now if we increase the frequency, then we end up with a wave that looks like this. So this wave has a node here, there, 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 and antinodes here, there, and there. So let's look at these three waves, and let's say that the length of these posts here at the ends, that is L. So we want to express L as the number of wavelengths that we're seeing in the string. So let's remember what a wavelength is. A wavelength is the length of a pattern that repeats itself. So if it starts here and goes down and back up, that would be one wavelength. Well, that means that only this much, this part, is that part. So that is half a wavelength. So I'm going to write that L, the length of the string, here is lambda over 2, half a wavelength. Below, we have an entire wavelength, just like here. So the pattern would start repeating itself. It kept on going beyond. So I'm going to write that instead of L equals lambda, I'll write it as L equals 2 lambda over 2. Then in the next pattern, so this much is one full wavelength, and then that is going to be half a wavelength, just like we had over here. So L here is 3 lambda over 2. We have 1.5 wavelengths between the two ends. So how about we solve for the wavelength from here? So lambda would be 2L, and here lambda would be 2L over 2, and here lambda would be 2L over 3. So if we generalize, lambda sub n is going to be 2L over n. Now remember that the speed of sound is lambda times frequency, which means that the frequency is the speed of sound divided by the wavelength. So plugging in the lambda we found before, we end up with v over 2L over n, or nv over 2L. So the frequencies that we have on the string, this would be f1. So for n equals 1, then this would be f2 for n equal 2, and this is f3 for n equals 3. Now f1 has a special name. It's called either the fundamental frequency or the first harmonic. Then F2, F3, and any subsequent Fs would be called harmonics. So F2 is the second harmonic, F3 is the third harmonic, and so on. So here is a summary of this. F for a standing wave on a string is n times v divided by twice the length of the string, where n equals 1 corresponds to the fundamental frequency or the first harmonic, and n equals 2, 3, 4, and so on correspond to second, third, fourth, and so on harmonics. Now, if we're looking at longitudinal standing waves, so for instance, a pipe that's open at one end and closed at the other, we would have something like this. So I have a pipe of length L, and I'm going to draw a few of these. Here's a second and a third. So we know that at a closed end we have to have a node, and at an open end we have to have an antinode. So that is the case for all of these, and let's see how we can make this happen. Well, we can start at this point with a node and then start opening up until we get here. Then the next one, we can cross it here in the middle, so we have another node there. And then the third one would be something like this. So we have 1, 2, 3 nodes here, and then we have 1, 2, 3 antinodes, 1, 2 antinodes, and 1 antinode. So again, we want to write L, the length of the pipe, as a function of the wavelength. So let's draw a wavelength again. That's one full wavelength. And compare what we have here with the full wavelength. Well, it looks here like we're starting at a node and then only going to its maximum displacement from equilibrium, to its amplitude. Well, that corresponds here to only this much, and that will be a quarter of a wavelength. So L is lambda over 4. Then for the second one, we're going up, back down, so that's this much, and then we're only going back to an antinode, so that would be here. So this is half a wavelength, and that's another quarter, so we have here L is 3 lambda over 4. You can probably guess that the next one will be 5 lambda over 4. So this is one full wavelength, and then that would be a quarter of the wavelength. So L is 5 lambda over 4. So if we kept going, we would end up with L equals, so here we have 1 lambda, 3 lambda, 5 lambda, all divided by 4. So this will be n lambda over 4, but n is 1, 3, 5, 7, and so on. So it's an odd number. So remembering that V is lambda F, and lambda is from over here, lambda is 4L divided by N, 4L divided by N. There we go. And we want to solve for the frequency. So frequency is V over lambda. So that would be V divided by 4L over N, or frequency would be NV over 4L. So that is the frequency, and we have to remember again that N is 1, 3, 5, 7, and so on, odd integers. So back in the diagram here, we would have F1, F3, F5. So F1 is the fundamental frequency or the first harmonic. F3 is the third harmonic. F5 is the fifth harmonic. So longitudinal standing waves wave where the pipe is open at one end and closed at the other does not have second, fourth, sixth harmonic. It only has odd numbered harmonics. So here we're summarizing this. So F is NV over 4L. N equals 1 corresponds to the fundamental harmonic or the first harmonic, and then the third, fifth, and seventh corresponds to third, fifth, and seventh harmonics. Now, if we had a pipe open at both ends, so let's say that it looks like this, and then we have a second one. The first pattern we can have has to be open at both ends, so it would probably go like this, because we want it to be open at both ends. The second one, again, open here and there. So the second pattern looks like this. So what we have in this situation is L is equal to lambda over 2. L is equal to 2 lambda over 2. And we end up with the same equation we had for standing waves on a string. So if we have a pipe open at both ends or a standing wave on a string, we get the same types of frequencies for these two situations. Now, there's something called beats, a beat frequency, and that happens when two sounds that have very close frequencies and they sound at the same time in the proximity of one another, then the intensity of the sound will fluctuate, and that's when we hear what we call beats. So the beat frequency is the difference between the two frequencies. So it's really the absolute value of F1 minus F2. It really depends. I mean, it doesn't matter which frequency is higher. What we're looking for is a magnitude. So the beat frequency would be just some positive value. And that's usually a very small frequency, like 3 hertz or 2 hertz or something like that. Now, a very complex topic is the Doppler effect. So the Doppler effect has to do with how frequency is perceived versus what the frequency of the original sound was. And that happens when we're dealing with sources that move really quickly. So we have various things to take into account. So we must have a source, the source that makes that sound, and we must have an observer. So in this equation, F prime is the frequency that's perceived by the observer. F is the original frequency of the sound. V is the speed of sound. So both this V and that V are the speed of sound. V naught, it's actually VO, is the speed of the observer, and Vs is the speed of the source. So there are 4 situations. We can have the observer moving toward or away from a stationary source, or we can have a source moving toward or away from a stationary observer. But if we combine the entire equation, we end up with something that looks like a monster. So we have V plus or minus V observer divided by V sound minus plus V source. So to interpret this, the top sign, so the plus sign up here and the minus sign over there, stands for toward. So the top sign would say that the observer is moving toward the source if we picked the positive sign. And if we pick the negative sign here, we would say that the source is moving toward the observer. The bottom sign, the negative here, says that the observer is moving away from the source. And here we would say that the source is moving away from the observer. So we can have both observer and source moving either toward one another or away from one another. So pretend that there is a car chase. So there is the siren of the police car, that would be the frequency of the siren. The source is the police car, and the observer would be the person that is being chased. So in this situation, we have the source moving toward the observer. So we have to choose the negative sign, whereas the observer is moving away from the source, is running from the police car. So we're using the negative sign here. So then the equation we would end up with is F perceived by the observer is the original frequency of the police siren times V minus V naught, because the observer is moving away from the source, divided by V minus V source, because the source is moving toward the observer. So this takes a little bit getting used to, but if you remember that the top sign stands for toward and the bottom sign stands from away, that would be quite helpful.